Let me begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for the students, this class. Just ask that you bless, be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. Let's see here. Yeah, see, now it's 2:15. There you go. So, I must tell you guys about power series today. So let us discuss power series and their properties. First of all, a definition. Power series centered at Z0. All right, which is going to be a complex number for us, of course. Is a well, I'm going to change it up from the notes a bit here. A function whose formula is given by a series. In particular, we have like f of z is equal to a sum, k equals 0 to infinity of a sub k times z minus z naught to the power k. All right. Where, you know, a0, a1, and so forth and so on, right, are elements of the complex numbers. All right. We say that a sub k are the coefficients of the series. All right. So here I would say that f of z is an element of the polynomials in z minus z naught. So like, for another example of this notation, all right, if I was to say g of t was an element of the polynomials in, say, t minus 3, I'll make it complex here for a second, 3i, all right, then g of t would be something like the sum, you know, n equals 0 to infinity of b sub n times t minus 3i to the n power, all right? So this is notation we can use. I don't think I even use this notation in the notes, but, you know, maybe I should. So generically speaking, a field with a bracket is a notation for polynomials in the field, in that variable, all right? In that variable. Now, power series, let's see here. So another example. Example 2, we could look at the sum k equals 0 to infinity of, say, 2 to the k divided by k factorial times z minus 3i to the k. All right? This would be a power series, right? With centered at z naught equal to what? With coefficient ak equals to what? So the center is 3i, and the coefficients in this case, 2 to the k divided by k factorial, all right? Now, I'm going to skip over the proof of the theory here because I'm behind, sadly. But we can prove that every power series has a radius of convergence. And so, in particular, we can make the following definition meaningfully, all right, which is that the sum k equals 0 to infinity of a sub k z minus z naught to the power k has radius of convergence, which I'm going to abbreviate ROC, R, if the series converges for modulus of z minus z naught less than r and diverges for modulus of z minus z naught greater than r. All right. So there are basically three cases to consider here, and the three cases are the following. You have so if this is, let me call this thing f of z. So we could have the domain of f of z looking like this. There you go, that's it. We could have the domain of f of z looking like this. Right? Or we could have the domain of f of z looking like, well, everything, right? Oh well, I tried. So this is r equals to infinity. My bad, opposite story, 0. This is, 0, r finite but non-zero, right? And this, of course, is the case r equals to infinity, where r is the radius of convergence. These are the three choices. Now, I've tried to be illustrative in my picture in the middle case, you see, because it may or may not be that the domain includes the edge, right? There are series which include the whole circle at the edge of the disk of convergence. There are ones which contain none of them. And there are others which contain a countable infinity of points, but not every point. I mean, there's pretty much anything is possible at the boundary. All right? Any questions? So the proof of this takes about 20 minutes to establish carefully. I'm going to skip it. Now, so the theorem then, next up here, is that, see if I even want to say this theorem. Let me just say it and not write it. Let be a power, if you have a power series centered at z naught, then the power series converges normally on its open disk of convergence. All right? It converges normally on its open disk of convergence. And it does not converge if you're beyond the disk of convergence, all right? So what did converge normally mean? We talked about this last time. It means that on any closed subdisk of the disk, we have uniform convergence of the series, right? But you don't necessarily have uniform convergence on the totality of the open disk of convergence. Did you get, so like in calculus 2, we talk about the open interval of convergence, which just doesn't include the endpoints. Here we might talk about the open disk of convergence. You see what I'm talking about? Like the open disk of convergence would just be the solution set to this over here. I'm off camera, but let's see. Try to do a lot of examples today. Example 3, geometric series, right? F of z equals to the sum k equals 0 to infinity of zk, right? Remember how this works out? This works out to 1 over 1 minus z for what? If modulus of z is what? Less than 1. We worked that out, right? Remember? So what's the radius of convergence here? The radius of convergence is r. Yeah.
Wait, yeah, it is r.
It is r. That is a reasonable answer to my question. It's just not the one I was expecting.
Me neither.
So yeah, this is equal to r, is the point, yeah. For r, the radius of convergence. And in this particular case, the open interval of convergence, right? It's entered at 0. That is the domain of f in this context, right? That's it. I mean, there's no points on the edge of convergence, right? Because if you put in something with modulus 1, then the series diverges. All right. What if we do something a little bit different with this example? Let me show you something we could try out here. What if I was to look at, say, well, this time, let me say g of z equals to 1 over 1 minus, and I should be, let me not say, this is not g of z yet. My bad. I'm going to start with this. And I'm going to rewrite this as, like, I don't know, 2 over 2 minus 2z, right? I can do that. I just multiplied by 1. And then I'm going to rewrite this as 2 over 1 plus 1 minus 2z. I can do that too, right? So I've not done anything terribly suspect here yet. I'm going to factor this 2 out for kicks. I've got 2 over 1 minus, I'm going to factor a minus 2 out actually. So 1 minus 2 times what? Times z minus a half apparently, right? Do you guys agree? All right. Now I'm going to let g of z equal to the sum, k equals 0 to infinity of 2 times 2 times z minus 1/2, parentheses to the k. And then I'm going to ask you a question. Is this a power series? No, incorrect. It's almost a power series. A power series for us has the specific form k equal, now you'd be like, well, you're just being a stickler. Well, that's true. But so we have 2 to the k plus 1, right, times z minus z, my bad, z minus 1/2 to the power k. Now, with that, we have a power series. So the power, it's not just a function that, like, when I say power series, I'm not just saying that the function can be written in the form of a series. I'm saying it is written in the form of a series. I know there's kind of like a, so that's why in my notes are somewhat better because I just say it's an expression. A power series is an expression of the form. Maybe that's a better language, all right? Because indeed, this is, I mean, these formulas are equal, but I'm saying that this one's a power series, when this one isn't. What I'm pointing out is that this one has z minus z naught to the power times the coefficient. See here, there's a 2 wrapped up into the power k. It's important for certain theorems that we actually reformat it specifically in the format of a power series. So now that I've done this, you can identify that the coefficient in our language is a sub k is 2 to the k plus 1, and the center is 1/2, right? Now this is equal to 1 over, well, this is equal to 2 over 1 minus 2 times z minus 1/2 by the geometric series result, right? I'm using the geometric series result of the following form. You know, the sum k equals 0 to infinity of a times r to the power k is a over 1 minus r that's true if the radius of the geometric series, or the ratio, whatever you want to call it, is the modulus is less than 1. Like this is the geometric series theorem. Now by the algebra that I invented this example from, what's this equal to? 1 over 1 minus c, right. All right. But what's the, what's the radius of convergence here? Or more to the point, that red equality I wrote there, where is that, what are the terms and conditions on that equality? Because there are some, right? There'd be fine print right here. What is the fine print? We need what? We need that the modulus of 2 times z minus 1/2, right, has to be less than 1. See, because going back, that was the r for the geometric series, right? So I don't need any kind of fancy schmancy convergence test or anything to figure out the radius of convergence for a geometric series. I use the geometric series result. I just have to understand what is the ratio of the series, and from that I can directly read off what the radius of convergence is. Now I'm not quite there yet, right? Because this doesn't quite give me a direct geometric picture of what's going on yet. I divide by 2, then I've got modulus of z minus 1/2 is less than 1/2, right? So apparently the radius of convergence for this one is what? Not 1, but 1/2. But it's the same function. How can the same function have 2 different radii of convergence? They're both 1 over 1 minus c. What gives? Why does the one radius of convergence 1 and the other radius of convergence 1/2? Aren't they the same function? See, they're not the same function, are they? They both represent the function 1 over 1 minus z. But as power series, these are different power series. The power series g of z and the power series f of z, these are 2 different functions. They have different centers. This one's centered at 0. This one's centered at 1/2. They're genuinely different functions. I perhaps should actually, but it's a question of domain, right? This equals 1 over 1 minus z on the unit disk, open unit disk. This equals 1 over 1 minus z on the open half disk. Let me draw a picture. So if we think of h of z as the function 1 over 1 minus z, what's the domain of h? Everything except what? Except z equal to what? 1, right? So it's got a problem right here, right? This is the trouble spot, right? Everything else is in the domain of h. If I picture, example 3, here's the domain, right, of f. That's the domain of the power series representation of h centered at 0, right? And on the other hand, this one is centered at 1/2, right? So what happened? That's the domain of g, yeah. All right, so we have to make a distinction. Like, I know it's a little bit subtle, but there has to be a distinction made between the power series and sometimes like the function it represents, right? There's something else we could do. We could take the given power series and like move it, right? Like what would happen if I tried to take f of z, right? If I tried to take the formula for f of z and shift, what if I would try to take the formula for f of z and I like shifted the center of it from 0 over to like -1? What if I tried to shift whatever that means, center of, power series f of z from 0 instead over to, say, z naught equals to -1.
Would you just use a Mobius transformation?
Oh, that's too fancy for me right now. Maybe. I was thinking of something much less glorious, which is I take my sum z to the power. I'm going to use n instead of k just for change of pace here, if that's okay with you guys. My n's are way prettier than my k's. So sum n equal, your k's are n's, but I'm fine. Sum n equals 0 to infinity of z to the power n. How do I change that to be centered at -1? What could you do? What if I did z plus 1 minus 1? That's true, right? And then if we want to get nuts, we could try to do this calculation. I probably shouldn't. I'm misbehaving at the moment if you guys hadn't figured it out. Sum n equals 0 to infinity of so what would this be? I mean, we'd have a z plus 1 to the n, right? Minus n times z plus 1 plus dot 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 dot. Well, eventually plus -1 to the n, I guess. Because that's something to the nth power, so it expands like that, right? I mean, you have to use binomial theorem to make this careful. But what I'm arguing, and I don't want to do this in class because this is really off the beaten track, but you can actually make good on this idea of shifting the center of a power series. This is called analytic continuation, which is not something I'm going to cover carefully this semester, so I just figured I would get over with right here. But basically the idea is, what if you were to shift the series center by this if you were to do this, then what's going to end up happening is, you're going to have a center over here, right? And after you do this algebra and simplify things, what you're going to end up with is something that has radius of convergence not 1 anymore, but now 2. And the recentered one is going to have, like that. And so I can tell you, I don't want to finish this calculation, but I could tell you what's going to end up happening here, because I could simply rewrite h of z to be centered here. That's easy to do. So h of z, 1 over 1 minus z, right? But instead of z, I do z plus 1 minus 1, like that. Which gives me, that's a 2, right? 1 over 2 minus z plus 1, which we factor out a 2 here. We'll do it here. So that's, I'm going to put the half up top. 1/2 of 1 minus z plus 1 over 2. All right? Now I'm geometric. That's geometric. That's the geometric summation. And so I can go straight from that to, I'll pull the half out front if you guys don't mind. 1/2 the sum n equals 0 to infinity of z plus 1 over 2, big parentheses here, to the power n. Which, one more step here, this would be the sum n equals 0 to infinity of 1 over 2 to the n plus 1 times z plus 1 to the power n. What's the radius of convergence? So just to be clear, not obvious. All right, this is not obvious. That would be a page of calculation for me. All right, but I know what happens. I know what happens because these are all of the power series on this board are just different representations of this single complex function h choosing different centers. So all of those different power series, they're going to agree wherever they overlap because they're commonly, they're joined together by h. Yeah.
Oh, this might be a stupid question, but the equation in green, so the h of z,
Yeah.
how is that what you did there, and then at the end of that, you did to a geometric series, like what's the difference between, like why is the green equation not a geometric series?
Well, this is not a series,
Oh, okay.
and this is not a series, and this is not a series. None of these are series.
Okay.
But this has the right format. Like, I need to have the format a over 1 minus r, see? Once I have the format a over 1 minus r, I can identify, oh, a is the first term in the geometric series, and r is its ratio.
Oh.
The ratio for this one is z plus 1 over 2, right? So z plus 1 over 2 less than 1 is what? Z plus 1 less than 2, which is exactly what I said would happen. The radius is 2 when we center it at minus 1. All of this without Taylor's theorem, the ratio test, anything. Because all of these things are already there to discover with just the geometric series here. I cannot overemphasize the importance of the geometric series, but I must go on, as there is more to life than the geometric series, right? So, so theorem, I'll just state it briefly. We can differentiate and integrate power series term by term. Hopefully you already saw this in, calculus 2, right? It's still true here. Do you remember how the radius of convergence was related before and after differentiation or integration of a series? No? Well, it's an easy thing to forget because it's not very interesting. The answer is it stays the same. So, yeah. Now, and so the proof of these assertions basically rests on the uniform convergence of power series. Power series are built from sums of power functions. Power functions are holomorphic everywhere, which means that they're continuous, they're a uniformly convergent series of functions, and as such we can pass the derivative inside the summation, and we can exchange the order of like integration and summation in short. So let's see here. So that's one thing. So let's let f of z. So this is a calculation we should all do. F of z equal to, the sum. I'll use n this time. N equals 0 to infinity of like an times z minus z naught to the power n, right? So what's f prime of z? So I said you do it term by term, right? So the way that works out is the sum n equals, well, 1 to infinity, right? Of n times an z minus z naught to the what? To the n minus 1. Oh, you wanted to know what we were doing tomorrow in differential equations. This. Yeah, series. Isn't that funny? It's kind of funny. Timing is kind of funny. Yeah, it's not by design. It's just, there's a certain, order to the music of mathematics, and it just so happens that You get to the same part in the different pieces. Anyway, n minus 2, like that. And you can keep doing this. And of course I should put n equals to 2 here. You don't have to put n equals to 2, right? I could just keep leaving these at 0. Wouldn't be wrong, right? What am I doing though? I mean, if you start those at 0, it's just the first term is 0, then the first 2 terms are 0 because, 0, and then, all right, anyway. And this continues, right? What's the kth derivative here? I'm going to start it at k because that's really where it starts, if that's all right with you guys. So we'd have n times n minus 1, and then you'd have n minus 2, and so forth and so on until we get finally to n minus what? N minus k is almost right. N minus k plus 1, right? So you could either write this as n minus k plus 1 like that, or you could put parentheses and do n minus parentheses k minus 1, which would also be true. That is the pattern. And then, of course, we've still got the a sub n and z minus z naught to the power n minus k. All right. What happens when we evaluate what's f of z naught equal to? What's f prime of z naught equal to? What's f prime prime of z naught equal to? What's the kth derivative at z naught equal to? What happens when you plug z naught into the power series?
It's always 0.
It's always 0, except where? Like this, more explicitly, is a0 plus a1 times z minus z naught, right? This one is a1 plus 2a2 z minus z naught, yeah? This one is a2, excuse me, my bad, 2a2 plus 3a3 z minus z naught, right? So what you get is a naught, a1, 2a2. Let me rewrite this somewhat silly way. That's 0 factorial times a naught. This is 1 factorial times a1. This is 2 factorial times a2. It would have been more exciting if I had given you the third derivative. There we would have had 3 times 2 a3. Ooh, looks like you really did something there. 3 factorial a3 is what you got there. And this one, of course, you end up with k factorial times a sub k. You put this all together, and you observe the pattern that the nth derivative at z naught is simply equal to, divided by n factorial, is the formula for a sub n. So if you have a power series, right, and you have a formula for its coefficient, its nth coefficient, then you know the nth derivative at the center of the power series. It's right there, staring you in the face. It's just there, right? You just got to adjust for the factorial, but that's it. So this leads us to, of course, Taylor's theorem, which is simply that f of z can be written as the sum n equals 0 to infinity of the nth derivative at z naught over n factorial times z minus z naught to the power n, right? Although what's the precondition to the theorem in its current formulation in our current discussion? What did we assume about f of z going into this? It was a what? Assuming f of z is power series centered at z naught, right? That was the condition, the big condition we assumed at the start of this derivation just now, right? So I should probably say a little bit more about the theory of convergence and divergence for power series. I don't seem to have, well, I brought my book with me. So if you guys look in chapter 5, Mathematical Theory of Convergence, on page 265, a formula is given, a stone cold formula for the radius of convergence, all right? And so I guess I'll put it here. And the formula is this. This is again from page 265 of the textbook, all right? And the formula given is this. The radius is equal to 1 over the limit superior, lim sup, of the nth root of the modulus of a sub n. This is for, power series n equals 0 to infinity of like a sub n z minus z naught to the power n. That's the radius of convergence. You just have to take the limit supremum of the coefficients. This is what's known as the Cauchy-Hadamard theorem. You guys probably don't know what the limit superior is, right? No. So what you have to so what this thing is you have to think about all possible subsequences. All possible subsequences, and you pick the supremum of all those possible subsequences. All right? So the least upper bound of all the possible subsequences. This is more nuanced than the ones you see in Calc 2, because this works when the series has infinitely many terms which are 0. Right? We also have the ratio test. Like we can say that. I can say that more plainly. What's the ratio test? Do you guys remember that? What's the ratio test? If we have, trying to remember, let's use the letter B here for a second. Like B sub n equals 0 to infinity, converges. Well, then you can let L equal to the limit as n goes to infinity of what? The absolute value of, what is it, bn plus 1 over bn? I can't remember, guys. You have to help me out. Like, it's been a minute since I taught Calc 2. I can't remember. Does the n plus 1 go upstairs or downstairs?
I think it's downstairs.
Downstairs?
Because you want it to be 0, right?
Well, we want it to be less than 1.
Right.
I think it has to be upstairs, because if it's less than, yeah, less than. So if this is less than 1, that then implies that, oh man, I have to erase this. Sadness. Then the series n equals 0 to infinity, b sub n converges absolutely. Or you could say it's absolutely convergent, right? So what does this theorem look like when you apply it to a power series? Yeah? So this is still true for complex series. The ratio test is still true for complex series for pretty much the same reasons as it was true in Calculus 2. With absolute values being replaced by moduli, the proof is essentially the same, all right? And as with most things, the proof rests on the geometric series. Go figure. But if we apply the ratio test to a power series, like, so the power series, let's suppose we have, the sum n equals 0 to infinity of, say, an times z minus z naught to the power n, right? So that makes this whole business right here my quote-unquote bn, right? If I'm going to apply the ratio test to this. And so we look at L, the limit, as n goes to infinity, the absolute value of like an plus 1 times z minus z naught power n plus 1 divided by an times z minus z naught power n, right? Well, do the math here on the absolute value stuff. I mean the modulus. Well, what you get is the modulus of z minus z naught. See, because these two cancel and just leave you one power. It's independent of n. You pull it out of the limit, you got the limit as n goes to infinity of the modulus of an plus 1 over an. All right? And so if this is less than 1, you have absolute convergence, right? Less than 1 is the condition for absolute convergence. That's what I'm interested in. Greater than 1 implies divergence. Equals to 1, you get nothing. You get no information at all, right? What does less than 1 say here? Solve this inequality for this. What is it? So first of all, if I call this thing, I don't know, Pac-Man, then I have modulus of z minus z naught less than what? I need it to be less than 1 over Pac-Man. So you can use the ratio test for complex series. And it turns out that the meaning of this limit, right, it's reciprocal to the radius of convergence. So that's kind of neat. But the shortcoming of what I just did with the ratio test, right? Think about this. What if your series is 0 for even terms? What if your series is 0 for odd terms? You have infinitely many terms which are 0. So you can't do this because you've got division by 0 out the wazoo. You know, it's no good. The way to get around that is to use the limit superior, which doesn't consider, it considers subsequences, all possible subsequences of the sequence. And it finds the sort of the supremum, the least upper bound of all those, if it exists. I'm not going to test you guys on this. I want to make you aware of the idea. Again, it's on page 265 of the text. But you should know the radius. You should know of course, I think you should know the ratio test, right? And I hope I've shown you enough here that you could apply it to a complex context, right? Like we could go back to this example here. What's the radius of convergence here? We could use the ratio test to figure that out, right? Like what's Pac-Man for this guy? I probably should come up with a better label for it, but we'd be talking about the limit as, I guess I'll change to k. K goes to infinity of what? Of 2 to the k plus 1 over k plus 1 factorial, right? And then divide by it, so multiply by the reciprocal. So k factorial over 2 to the k, right? Typical Calc 2 calculation. That's the limit as k goes to infinity of whale 2 over k plus 1, right? Also known as 0. In this context, what does that mean? That means that the radius, so this is equal to the radius, right, of convergence for the series in question. So what this tells me is that has a radius of convergence infinity. It converges on the entire complex plane. When that happens, the power series is said to be entire. This is an entire series. All right. Ah! Dare you. So what you're telling me is I need to get my revenge on Sprano.
Yeah, he put it there.
He put it there.
And that's why, like, you're used to it not being in that exact spot.
I'm going to put something that leaks very slowly on top of his man cave. It's going to drip, drip. He won't know where it's coming from.
I said you get sparkling water.
Ooh.
Get yellow food dye.
Oh, don't do that.
And then you just put the yellow food dye. And maybe a little blue. You have to test it. And put that, because the dye matters.
No.
You need the dye. Or just
No.
dump out half of it and then put sparkling
Oh,
water.
no, I'm not. No, it's sparkling water. I'm going to get Blanheim ginger ale. Do you know what Blanheim is? Do you know?
No,
Ah.
it's horrible.
It's glorious.
The color would be,
All right. I need to buy a case of Blanheim so we can drink some together.
awesome. You have to drink it first.
What does it taste like?
We have brand new open ginger ale.
Oh, well, that's not bad.
Tastes like fire.
Fire?
Tastes like fire.
He only drinks coffee and water. What do you expect?
I can drink water.
Sorry.
All right. So this, I hope you understood what I did here. These algebra steps I did here is something I expect you to know how to do. This is, well, that's what I'm asking. I should have just had 20 factor quadratic problems. It's just too depressing. I can't do it.
You might just like guess 1 and -1 and then.
All right. I'm gonna move on here. So definition, a function f of z is analytic on the disk of radius r centered at z naught, which I'll write out. So we're talking about z in the complexes such that the modulus of z minus z naught is less than r, right? If there exists a sub k in z complex numbers such that f of z is equal to the sum k equals 0 to infinity of a sub k times z minus z naught to the power k for all z in the disk of radius r at z naught. And it's analytic at z naught, right? If there exists some r positive for which it's analytic, right? So do you guys see the difference between this? I mean, we've talked about complex differentiable at a point. We talked about holomorphic, right? That means that there exists an open set on which it's complex differentiable at that point. And now we're talking about analytic. Analytic means that the function has a power series expansion. Okay? Here's the theorem. Suppose f of z is, holomorphic for modulus of z minus z naught less than rho, then f of z is equal to the sum k equals 0 to infinity of a sub k times z minus z naught to the power k for modulus z minus z naught less than rho, where what do you think a sub k is equal to?
Did you say A sub k?
Yeah, what's a sub k equal to?
Probably the k derivative of f over.
That sounds like a good choice. So the kth derivative evaluated at z naught divided by k factorial, that will be how we choose our coefficients, right? And what can you tell me about the radius of convergence? It's got to be greater than or equal to rho. Moreover, for any r that's less than rho, fixed r, all right? So just to draw a picture, rho is the, so we know, we're given that it's holomorphic on this green disk with center z naught, all right? So you're given that it has its complex differentiable up in here, right? And here R is going to define some circle inside there, right? Z naught's the center point here. Then what can you tell me? What have we learned? Well, we have also learned that this is equal to what? I'm going to put the conclusion up here, if you guys don't mind. Oh, fine, I'll put it down here. A sub k is equal to 1 over 2 pi I. I just hate writing down here. Integral over z circle, modulus of w minus z naught equal to r. All right, f of w over w minus z naught to z k plus 1 dw. And then this is my theorem 8.4.2. I also throw that, also the final finishing blow here, also if modulus of f of z is less than or equal to m on that circle of radius r, then you have a bound on the kth coefficient. The modulus of a sub k is less than, this is just Cauchy's estimate applied to this current discussion, really. All right. How do you think we're gonna prove this? If you're to say with the projector, that would be correct. But what's that?
Just like with Cauchy's formula.
Like with Cauchy's integral formula. Maybe. Well, yeah, actually, I think that's essentially the proof with Cauchy's integral formula. That's the starting point. So what did Cauchy's integral formula say? Well, let me look at it here. Yes. I will be hopefully talking far less about convergence tomorrow, though. We'll just be talking about how to calculate. like in differential equations with the power series. We do talk a little bit about domain, but we're mostly, whew, that was close. I almost had to edit something there. Woof.
I think a lot more than
The serious stuff in Jimmy was the
What was?
worst part.
The series part is not the worst part. The worst part is the Frobenius theorem.
Serious what?
The Frobenius theorem.
Can I see that, Jordan?
Oh, I should know that.
Your serious solutions for the next one. Singularity. Yeah.
Bro, we got this.
I like this in calculus.
This is not.
All right, so here is the theorem that I just wrote on the board and covered up now because I'm a dummy.
Wait,
What?
we have a test for Friday going into Thanksgiving break.
Why wouldn't we have a test going the Friday and going to Thanksgiving break?
It's better than the Monday after the frigid break, you.
I could move it up.
No.
I mean, I certainly can move the test up.
You can move it to Wednesday. Yeah. What?
Yeah, you are here.
No, I think the next one, so it doesn't even really matter.
All right. So Shane was correct. Like basically, the integral theorem, Cauchy's integral theorem, is going to be the one of the main ideas. But actually, it's a little bit sneakier than that even, because what we do is we essentially just start with f of w over w minus z, and then we make it geometric. How do you get from an algebra expression to a series? Well, you use the geometric series. See, so if I look at f of, this proof is very indirect, all right, so just hang with me here. F of w is over w minus z. Well, that's equal to f of w over w divided by 1 minus z over w. But this is the convergent, this is the sum of a geometric series with ratio z over w. So I can swap out this for that. And then bring the w back in. I've got f w z to the k over w to the k plus 1. So we're actually also given that the convergence of the above series is uniform for radius r by the conditions given here. And so we can expand Cauchy's integral formula into a series of holomorphic functions, because this is straight up equal to that. I've got an integral of a series of holomorphic functions, which means I can exchange the order of integration and summation by the mathematics we looked at last class. And upon doing that, lo and behold, power series, we just proved holomorphic implies analytic, where the coefficients are straight up given by the integral that I had written. And then we know Cauchy's generalized integral formula, so we also know that this is equal to the kth derivative divided by k factorial. But to look at it a different way, suppose that you didn't know Cauchy's generalized integral formula. Well, excuse me, this is a little bit, there's still a substitution that needs to be made. This is just the theorem at 0, right? So notice though that if you did know Cauchy's integral formula, you could go through this calculation and you discovered that the kth coefficient of the power series is this. But since everybody knows about power series coefficients being related to derivatives, that would immediately give you the formula that this is equal to the kth derivative of f at 0 divided by k factorial. In other words, Cauchy's integral formula and the geometric series paired with this calculation reveals Cauchy's generalized integral formula. We derived it by exchanging the order of summation and differentiation. I mean, integration and differentiation. We formally derived it earlier, like a week or two ago. But this is yet another way to understand where Cauchy's generalized integral formula comes from. Here's a so that just proves the theorem is z not equal to 0. To prove it at z not equal to 0, I will show you the same argument, but this time